Okay, this is lesson 6.2 supplement in the BC course, but part 1. We talk about inverse trig functions. Well, the question is, how do we find the derivatives of these things? So, to use the inverse trig function, I think a lot of you recognize this notation from pre-calculus 12, but sometimes they use actually this name, the arcsine. So often you can also see this as y equals to arcsine of x. Okay? Why is it defined this way? Because the exponent of -1 sometimes gets people thinking of reciprocal, and that's bad because that, of course, is equal to cosecant x, and that's not what I'm talking about here. Okay? If that is the case, you are looking at sine x all to the power of -1, not sine -1 of x. Once again, sine -1 of x represents arcsine. Okay, that's like the inverse sign of the shift sign button on your calculator. Okay, now we've got a problem though, because the problem with finding the inverse function to sine is that the sine function is not what they call one-to-one. You're like, what's one-to-one again? Well, a function in which not only is there only one y for each x, but there's also only one x for each y. The graph actually has to pass not just the vertical line test, but a horizontal line test as well. So remember the sine function, right? It's like, it repeats itself. Notice how there are multiple x's for each y value. Okay, that's a problem. So what we have to do in order to be able to find the derivative is we need to actually restrict the domain of the original sine function so that the inverse actually will exist. Because if I were to take the entire graph like this and then do the inverse, I get this lovely thing, right? And that graph definitely is not a function because it doesn't pass the vertical line test. So in order for us to do that, we limit it, and this is the convention that the math people have come up with, we limit the domain and range of the original sine function to be -pi/2 to pi/2. The range, of course, from -1 to 1. And that then allows our inverse to also have the domain of -1 to 1 and the range from -pi/2 to pi/2. And therefore, it will definitely be a function. So now, knowing that, having that restriction, we can then say, hey, sine is continuous. The inverse of sine is also continuous. Also, since sine is differentiable, then, of course, the inverse of sine is also differentiable. So the question is, how do we actually calculate the derivative of arcsine? Well, we'll do it the following way. I don't know the derivative of arcsine, but I do know the derivative of sine. So what I want us to do, first of all, is just take sine on both sides. So sine of y equals to the sine of the arcsine of x. So once again, these are two functions that are inverses of each other, so when you do them back to back, you are just left with x. And you're like, well, why is this helpful? It's helpful because now you can take the derivative of this statement implicitly. Do you remember implicit differentiation? Here we go to review some previous concepts. The derivative of sine, of course, is cosine, so it's cosine y, but because y is a function of x, we have the extra little bit that comes out, an extra factor of dy dx, or y prime. And the derivative of x, of course, is 1. Well, this is nice because I want you to solve for dy dx. I want you to find the derivative. So the derivative just becomes 1 over cosine of y. Now that is correct, but unfortunately that's not what I want because our original function was in terms of x. So the question I have for us now is, how do we figure out what this cosine of y thing actually is in terms of x? Well, that requires us to look back at this statement. Okay. What does this statement say? Y equals inverse sine of x. That means if I were to draw a right triangle, okay, that y represents what? Is it a ratio? No. It's the actual angle. So let me call y the actual angle. And so if I have y as the angle, what is the actual ratio here? The ratio is that the sine ratio is defined as x over 1. Remember what sine is defined as? Sine of the angle is the same thing as opposite over hypotenuse. So in this case, I told you, the sine of the angle has the ratio x over 1. So the opposite side of y, that would be here, that must be x. The hypotenuse must be 1. And therefore, using Pythagoras, I can solve for the remaining side. I believe it's just 1 minus x squared. That makes sense? I certainly hope so, right? A squared plus b squared is c squared. Do the algebra, that's what you get. Now, why is this diagram important for me? Remember our goal was to figure out what cosine y is? Well, cosine y is defined as the adjacent side over the hypotenuse side. All this trig stuff from way back in grade 9 and grade 10. So the adjacent side in this case now is the square root of 1 minus x squared, and the hypotenuse is 1. So ultimately, cosine of y is the same thing as the square root of 1 minus x squared, and I can make that substitution now, and then lo and behold, I have my derivative in terms of x. So what you have to memorize and know now is that if the function is the inverse sine, its derivative is 1 over the square root of 1 minus x squared. Done. Okay. Now, when you turn the page, you're going to have to do the same thing for arccosine and also arctangent. Once again, we have to limit the domain of the arccosine function and the cosine function. In this case, for cosine, we do the domain here of x being between 0 and pi, where the range, once again, is -1 to 1. And therefore, when I do the arccosine function or the inverse cosine function, notice that the domain is now -1 to 1, and the range is, in this case, from 0 to pi. Okay? So, follow the same process as before, and let's see if you can figure out the derivative of arccosine. Take cosine on both sides. I'm going to shorten this up and just write down x. Find the derivative of cosine, which is negative sine y. Don't forget implicit differentiation, dy dx. So dy dx just equals to -1 over sine of y. That picture that comes from this statement here, y. Cosine this time, so adjacent over hypotenuse. Figuring out this missing side here, that now becomes 1 minus x squared. And so if you look at sine of y, it's the opposite over hypotenuse. The opposite just happens to be that square root again. This time the function is negative. So if you want to memorize, if you have the arccosine function, its derivative is not just 1 over 1 minus x squared, but the negative of it. Very similar to arcsine, except with the negative. Okay? Yeah, if you got that, bravo. Now I want you to do tangent, or arctangent. Okay? I'm going to leave this one up to you, because it's pretty much the same process. So I'm tired of talking, and I know you love practicing. So therefore, you just need to go and try it yourself. Okay? All right. Don't wait for me. Go. Oops, no equal sign. Alright, here we go. Same procedure. Take tangent both sides. What's the derivative of tangent now? Aha, secant squared y. That's an extra dy dx. Solving for dy dx, I get 1 over secant squared y. Draw my lovely triangle. This time it's tangent, so opposite over adjacent. which means hypotenuse now is the square root of 1 plus x squared. Secant is the same thing as 1 over cosine, so that's hypotenuse. So secant y is the same thing as hypotenuse over adjacent. Hypotenuse is the square root of 1 plus x squared. The adjacent is 1. So, making the substitution for secant y, don't forget to square it. Ta-da! There you have it. So, as a summary, if you have the arctangent function, its derivative is 1 over 1 plus x squared. Memorize that, and you'll definitely need to use this for the next supplemental lesson, 6.2 part 2. And I hope to see you there soon.